Welcome to this explainer, where we are embarking on an incredibly fascinating mathematical journey. Today, we're going to decode the abundance conjecture, which, as you know, is a notoriously difficult open problem in algebraic geometry. But we're going to attack it through an entirely different lens, the Adelic Langlands Program. By the end of this explainer, you'll see exactly how abstract geometry translates into high-level number theory, and finally, right into the thermodynamic equations of physics itself.
To navigate this incredibly dense subject, we'll follow a 5-step translation process: the geometric problem, translating to spectral data, Iitaka dimension and weights, Grothendieck-Riemann Roch metrics, and thermodynamic phase transitions.
All right, part 1, the abundance conjecture explained.
So let's set the stage. The foundational goal of the abundance conjecture states that if a projective variety is minimal, meaning its canonical divisor is nef or numerically non-negative, its canonical class absolutely must automatically be semi-ample. In pure geometry, this semi-amplicity guarantees that for a large enough integer, the system becomes base point-free, which allows for a perfectly smooth structural contraction known as the minimal model fibration. But actually proving this purely through geometry, that's been a monumental headache. So let's flip the script and dive into a new framework. We are reframing the minimal model program entirely. By translating that combinatorial search for polynomials, represented by the mkx you see here, directly into the Universal Cosmic Partition Function xiologos of S, we literally turn a geometric roadblock into a hunt for smooth, unramified ground states in a macro-scale thermodynamic system. It's a total paradigm shift.
Which brings us to section 2, translating to spectral data.
This brilliantly illustrates our core mathematical dictionary. Check out how the geometric canonical line bundle translates directly into a global automorphic representation. Those linear sections, they become fixed Heckean variant vectors. But most importantly, bounding our geometric nef threshold directly forces the local Frobenius-Satsuki parameters to be less than or equal to 1. That's absolutely crucial because it locks the poles of our partition function safely on or just to the left of the critical boundary.
Now, focus your attention on the local partition function equation in the center, and notice the Swan conductor bottleneck mapped out right below it. The formula for z sub p heavily depends on the local Langlands parameter. If the abundance conjecture were to fail, hidden base loci would act as localized anomalies. And what happens then? The Swan conductor violently spikes, shattering the full symmetry of the local parameter and completely breaking the functional equation. System failure, basically.
To prevent that catastrophic anomaly, the program breaks the proof down into 3 spectral verification steps. First, mapping perverse sheaves via the Hitchin vibration. Second, executing a base change to bound the base loci. And finally, evaluating at the critical limit to enforce the global functional equation. The entire point of this sequence is to mathematically forbid those base point singularities, forcing the Swan conductor to exactly 0.
Okay, moving on to section 3, Iitaka dimension and weights.
The crucial mechanism here is this explicit translation law right in the center. Kappa of x equals the dimension of x minus lambda. Notice how beautifully balanced that is. Kappa, the Iitaka dimension dictating polynomial growth, is perfectly weighed against lambda, the highest weight parameter of the irreducible monodromy submodule. This single equation is what bridges the geometry of the minimal model fibration straight into the algebraic structure of the Langlands correspondence.
When we map out our 3 main mathematical universes under this translation law, things get really interesting. Observe how a general type variety, where kappa equals the dimension of x, forces lambda right to 0. This requires absolutely no nilpotent drift, locking everything perfectly onto the base space. Conversely, a Calabi-Yau variety forces a maximum weight filtration, which encodes some highly complex internal topological cycles. Let's unroll the local canonical product equation for sector 6. It reveals a really strict boundary. Think about it. If the Iitaka dimension were a fractional value, it would force non-integer weights into the SL2C factor, injecting a fatal algebraic glitch into this equation. But the universal functional equation strictly forbids this. By requiring exact anomaly cancellation, the math physically mandates that the minimal model fibration stabilizes into a clean, integer dimensional base.
Section 4. Grothendieck-Riemann Roch metrics. To make this fully rigorous, we have to physically metricize these abstract spaces using the Arithmetic Grothendieck-Riemann Roch theorem. And the expanded formula here, zero in on the arithmetic Todd class in the middle term. This isn't just some abstract mathematical operation. This is literally injecting external gravitational backreaction directly into the number field. It allows us to push infinite dimensional traces down to a rigid arithmetic base.
By pushing down that Arakelov metric, we integrate out the analytic torsion to generate this effective macroscopic metric, the Quillen metric, shown at the bottom. Because this effective spacetime metric is locked in by topological invariance, any attempt to distort a classical geodesic creates a non-zero differential phase error. And guess what? The global functional equation forcefully rejects that error, locking the geometry permanently into place.
Finally, Section 5. Thermodynamic phase transitions.
Using our new thermodynamic dictionary, we can view a failed, chaotic abundance state as a high-temperature, disordered phase, just boiling with infinite-dimensional p-adic noise. But as the system cools into the ordered phase at low temperature, the minimal model fibration is strictly enforced. It sheds all of those unstable degrees of freedom to leave us with perfectly smooth geometry.
Let's treat our complex scaling variable S as inverse temperature. Look at the equation for global free energy. It reveals a severe logarithmic singularity right as we approach the critical edge of 1/2. The free energy, F of S, scales as 2m times the natural log of S minus 1/2. That massive pole is physics telling us our mathematical structure is hitting a critical phase boundary.
Now, taking the second derivative of the free energy gives us the specific heat, CV, which scales to m over 2 times the quantity S minus 1/2, squared. Because it diverges quadratically at that exact critical edge, it mathematically guarantees a second-order geometric phase transition. It massively condenses all our arithmetic zeros and locks the order parameter into place.
And this brings us to the grand conclusion of this explainer. The exact mathematical requirement that forces the Swan conductor to 0 to eliminate the mass gap anomaly is the exact same requirement that proves the abundance conjecture. The minimal model fibrations of algebraic varieties aren't just combinatorial tricks. They are macro-scale thermodynamic ground states driven entirely by the functional equation's absolute need for stability.
I'll leave you with this final kind of mind-blowing thought to ponder. If the smooth space-time geometry that we rely on emerges strictly as a zero-entropy, error-correcting output of high-level number theory, well, what other fundamental truths of physics are waiting to be decoded in these equations? Are physical laws really just the universe naturally canceling out algebraic anomalies? Keep exploring that idea. Thanks for joining me on this explainer.